All right, let's make sure we have audio. Looks like we do inside OBS at least. Let me this preview. Let me shuffle the chat to the top here, and then we are ready to get going. So quick note, I know obviously this is normally the time for deep dive, Scott's stream, but Scott's out for the rest of the year, taking some certainly much earned time off. So I usually stream on Saturday mornings, but sometimes when Scott is not around on Friday, I will fill in during this time slot for a deep dive. So if folks have never caught my stream before, I do work on similar kinds of stuff, I would say, although generally I'm working more in Python land rather than in the core. Scott obviously spends a lot of time in the core. Occasionally I will dabble a little bit in there, but the majority of my streams are more on the Python side of things. So a little bit higher level. One thing I will mention, I know that normally during the deep dive stream, Scott has got the chats, YouTube and Discord pulled up on the screen, and I have just Discord down there. And I am also trying to keep an eye on the Twitch chat. I generally am unable to really keep an eye on YouTube as well. And I think that I finally figured out how to actually disable the YouTube chat. We were getting some unfortunate things spammed in the YouTube chat during the streams, and I dug around in the settings, and I think that I figured out how to turn off the YouTube chat. So I don't believe there is YouTube chat anymore, but I do have the page pulled up, and I will try to keep an eye in case chats do pop up over there. But I would definitely encourage anybody, if you are trying to ask a question or get a hold of me to make a comment or talk about anything, the best places are the Discord in the live broadcast room, which is what's on the screen below me, and then the Twitch on twitch.tv/foamyguy_Twitch, which I linked above as well. Those are the two best places to get a hold of me if you want to chat during the stream. So let's do a quick introduction as well. I will be working on CircuitPython stuff. If you don't have any idea what CircuitPython is, this is a good place to start, circuitpython.org. This is the website for it. This is basically a version of Python that runs on these tiny computers, like this one here that I have on the camera, which is a, what is this, an RP2040 Feather, I think? Yeah, Feather RP2040. This is essentially a tiny computer inside this little chip here, and the computer is able to talk to all these different pins that are along the side of this thing here. So it can communicate with external hardware like lights and buzzers and buttons and beepers and all kinds of things like this, sensors. It also has a couple of interesting things built on. This one's got a NeoPixel built in. And it's got a stemma port for you to connect more stuff up to it. And this one is a RP2040, so it's got like the PO system built in. It can do some crazy fast stuff with that. Different types of these microcontrollers have different things built in. There's a bunch of them in the backgrounds here on circuitpython.org. So one thing you can see is they come in all different shapes and sizes. But what brings all this together is all of these little devices support CircuitPython. So if you install CircuitPython on them, they show up on your computer as a thumb drive, basically, a little drive where you can save a code file. And then the microcontroller is always watching for that file. And anytime you update it, it will just automatically run the new version of your code. Yeah, hey there. Torgny, is that, I'm probably maybe not pronouncing it right, Torgny. And also hello to Paul SK. Let me get this one plugged in, actually. Let's start there. Get the USB cable here. I'll turn this around as well. I'll finish up the introduction also in a minute as well. I'm getting a little sidetracked, but let's do this. Nice. Yeah, thanks for tuning in. Hey, I appreciate all of the stuff that you have been working on lately. You've been kind of diving into the CircuitPython world, working on lots of display I/O and interesting stuff with networks and all kinds of stuff like that. So I'm always happy to see folks getting involved. So cool. It's nice to have you around and working on stuff. I appreciate you hanging out, tuning in, and also just hanging around the Discord and working on stuff. So let's see. Yeah, this is a version of Python. It runs on these little things. That's what we're going to be working on. Specifically today, what I'm working on is this EEPROM Breakout. I think it's this one. I'll pull it out here in a minute. I think it's this one. But this does not currently, as far as I can tell at least, this does not currently have a CircuitPython driver. They have a list here, a link rather, that says for Arduino you can use this library. So I'll go ahead and pull this up, and I suspect we'll be referencing this thing quite a bit. We're going to try to make a CircuitPython driver for it, which will be a bit of an adventure. I've never actually made a driver for low-level like I2C or SPI device before. I've worked on lots of different libraries, but generally the things I've worked on are a little bit higher level than the actual nitty-gritty communication between the microcontroller and like an I2C breakout device, which is what this is. So we'll give it a try. I don't know for sure if I'm going to be able to get it to working, but I am going to give it a try, and we'll see where we end up. If you want to get involved with CircuitPython, there's a couple of ways you can do it. On circuitpython.org, if you click contributing up here, this is going to take you to a list of all the open pull requests and all of the open issues. These are probably the two best places to get started if you want to get involved. On the pull requests, you can go through the pull requests. You can find one that interests you or that maybe you have the hardware to test for. Many of them are for specific hardware breakout devices. So if you have the hardware or you're interested in the library for whatever reason, you can go through and look at the pull request and leave a review. Look over the changes, see if everything makes sense to you, see if it looks good, spot like typos or misspellings or anything like that even. Try it out if you have the hardware and just leave a comment on that pull request letting us know that you looked it over and anything you found, and then if you tried it out, you can put that information as well. And that's a really good way that we like to get folks who are new involved. So that's pull requests. Open issues, this is a little bit deeper. In this case, you're actually going to be making your own pull requests. So these are open issues across all the libraries for CircuitPython. A lot of them right now are these missing type annotations ones. So that's kind of an effort we started back in October, and we're making good progress, but we still certainly have lots to do. So these are basically just adding the type information to all the functions inside of the libraries. So this is a good place, even if you aren't super experienced with Python, or if you haven't done a whole lot of stuff with CircuitPython yet. This is a good thing to start on because you really just have to look at the functions, look at the different arguments in there, and then determine like which types they're supposed to be and fill that stuff in. And if you do want to start working on any of that sort of stuff, and you need help, you can always head over to the Discord in the CircuitPython dev room or the help with CircuitPython room. There's plenty of folks around that are always willing to help folks get involved in reviewing and contributing. So this is the main place to head if you do want to get involved from like an actual development standpoint. Another thing you can do to support the project, though, is if you purchase hardware from Adafruit. So this is their website, adafruit.com. They are a hardware and software company based out of New York, and they are the folks that are providing the primary financial backing for the CircuitPython project. They pay the team that works on CircuitPython full-time. They pay me on a part-time basis to work on stuff related to CircuitPython. And so they are obviously a huge reason why CircuitPython exists and is able to continue existing and moving into the future. So they sell all kinds of different hardware. They sell the microcontrollers, sensor boards, and breakouts, and obviously lots of different NeoPixels and beepers and buzzers, and pretty much anything that you can imagine that you are able to plug into these microcontrollers and play with. They probably sell, pretty much anything you can imagine again. So check out their website. If you purchase your hardware from them, again, you are helping support the CircuitPython project, which is definitely much appreciated. So where I'm actually going to start today, Doc, how's it going? Yeah, love CircuitPython, done a really good job with it. Sure, there's bugs. Yeah, definitely. Supporting how many different hardware? Yeah, that's the thing. There's over, what are we at right now? There's over 100. I think we're close to 200, right? Or over 200. 258 devices that run CircuitPython. And these are just the microcontrollers. So there's also, another several hundred or possibly even thousands of different things that you can plug into the microcontrollers, different displays, different types of LEDs, buttons and beepers and sensors and everything, again, everything you can imagine. It is definitely a really, really tough nut to crack to actually keep all of this stuff working, and the team definitely does a really, really great job with it. There are going to be bumps in the road along the way. We always encourage folks to report, issues on GitHub, or even if you just come into the Discord and ask about it. If you don't have a Discord account or you don't feel like making an issue there, we always encourage folks to, let us know if they find stuff that's not working. But by and large, we try to keep it, so the vast majority of different libraries are working across all of these different, 258 and counting different devices. So definitely a big challenge, but a very fun one. And, I think the team does a great job. So I have never actually used any device like this little EEPROM Breakout. I think what I am going to start with is actually hooking up a different device, which is this spy frame, which I also have here. Although this one doesn't show. Oh, I'm not signed in, I guess, though, right? Is this the one I have? So I actually have this plugged in. Spy frame, it does look the same. I have the bag for it here. I'm going to try to make sure that I'm looking at the right page for the one I have. So this is 4718. Product code 4719, 4718. Just a different size, it looks like, from the first one. 2 megabits. So this is a similar type of thing to what our ultimate goal is. So let me actually pull up the one that is our other. This is what we're trying to make the driver for. I2C EEPROM Breakout 5146. Yep, that's the right product code. But I have one of these as well, which is a similar type of device. Both of these devices are persistent storage. They allow you to store your information inside of these chips, and they don't require power in order to retain the information. So even after you power down your circuit and unplug it, that whatever you wrote into the memory on these chips will stay there. You'll be able to read it again next time, and it will still be there. It will still have the same value in it. So that's what both of these devices are all about. And I want to start by looking at this FRAM, which I think is what ferroelectric RAM is what this stands for. I want to start with this one because there is already a CircuitPython driver for it. And because I noticed on this EEPROM page, which is the one we want to make a driver for, that it says down here, we recommend the FRAM and EEPROM library, which I opened up here, which has some stuff for FRAM and some stuff for EEPROM. So there's kind of two different parts to this library, one of each. And so based on all of that, again, I've never used any of this stuff before, but based on all of that, I'm assuming that they are, fairly similar in nature. And certainly from the user's perspective, I think we probably would want, either the exact same or really, really close to the same API for interacting with these two different things. And since this one does have a driver already, I'm going to hook it up, see how it works, play around with it for a minute. And then once I have got that experience, we will jump into the actual EEPROM one and try to make a driver to make that work. So we're going to hook this up. I'm going to go to the guide page for it, which is always a good place to start if you are using a new piece of hardware. So I will need to wire it up. We have power and logic. We want 3 to 5 volts, so it doesn't matter necessarily which power pin we use, I don't think. We'll go 3 volts on our feather. SPI, we have, let's check out the pins here. A hold pin, this is a wait pin for the SPI bus. When it's pulled low, it puts the bus on hold. It's different than the CS pin because it doesn't stop the current transaction. It's good if you want to talk to other SPI devices and stream data back and forth without stopping and starting transactions. I don't think I want to do that. I'm only going to have one device on the bus at this point, so I don't think we need to do this. So we might be able to leave out that pin. Clock pin we'll definitely need. MISO, I'm guessing we probably will need, and MOSI as well, because we're going to be sending some data both ways. We need to send it data that we want to write, and then of course it needs to send data back to us when we try to read it, so I assume we'll need both of those. Chip select pin, write protect pin. This is used to write protect the status register only. This pin does not directly affect write protection for the entire chip. Instead, it protects the block protect register, which is configured however you want. Sometimes only half the frame is protected. Okay, I'm not 100% sure what that means, but it is good to know. Assembly, I've already assembled mine. Really, it's just solder the little row of header on there. Let's jump down to here, CircuitPython, and we can see a nice wiring guide, so we will follow that. I think just, this is feather M0. This is using the hardware write protection, which I don't necessarily need to do. So the hardware write protection isn't necessary. However, hardware write protection could be useful with an external source of control, like a separate microcontroller. Okay, so I don't think we need the write protection. So I think this is the wiring diagram we're going to follow. So let's wire that up. I will try to split this up a little bit. I know the chat's going to be covering part of the screen here, so you all can't see 100% of all of this, but hopefully we can get some of it visible at least. Maybe I'll scoot them around the other way, since this one is empty at the bottom where the chat's at. There we go. Okay, so power. And I have a couple random wires here from the last thing I plugged in. Let's unhook all of those and start fresh. We have a green wire too. I have a couple more wires here if we need to get them as well. So let's see what we're looking like here. 3 volts and ground. We can do those first. I have a red wire for that. So let's go. We have 2 3.3 volt pins, so we'll just choose either one. Doesn't matter. I'm going to scoot this a little closer. There we go. 3 volts is going to go to VIN. Maybe I'll scoot it just a hair closer. Again, actually, let's go all the way. Wires are a little bit short, and since we're going on the long edge anyway, we got plenty of room. This. There we go, ground. We only have one ground pin, but it looks like we only need one connection right now, so that's okay. We could, of course, jump it over to the rail if we needed more, but ground. Ground here. Right next to 3 volts. Okay, and then hold pin is next, which we are skipping, and write protect is on the end, which we're also going to skip. I'm going to turn this around even though the wire kind of comes from the other direction. That way we can see this face up. And we might be able, let's see if we zoom in a little bit, we might be able to get slightly better focus. Let's see. Yeah, that looks better. All right. WP needs to be high. Okay, so thank you, Spider X in the Twitch chat there. So we may need to wire WP up to high. If it looks like we're getting write protected stuff, then we may need to pull that pin high. So I'll keep that in mind. Thank you. And it doesn't really matter what colors we use, but I do want to use 4 different colors if I can. Just try to keep it a little bit organized. We've got yellow, orange, and green. So white's the other color. Can use this white one even though it's longer. And we're going what? So SCK to SCK, that's pretty straightforward. I'll use white for that. And SCK on this feather is where? Let's see here. Right about there. Past 25. Here's this. Have hold. Oh, our ground is actually 2 over VIN. And then it's SCK. Yeah. So this is actually a little bit different of a pinout than what we have. Mine has got a 3-volt pin after VIN, which I think the idea is you can just pull 3 volts back out of it if you want to hook up something else. There is this photo actually too though, which is the one that I have, so maybe we should use this one. Yeah. We're leaving 3-volt open. We have power, ground, clock, and we need MOSI and MISO and chip select. So they use yellow for MISO. I'll follow that. I don't have a purple, but we'll substitute that one. So let me switch this back though, right? Let's put this one here. Back to the camera here. Yellow. There. I'll use orange for the other one, which is in between these. And chip select, they're using pin 5, and there are green there, and I have a green, so I'll follow that as well. Green. Select. Okay. And I'm just going to double check power and ground again, since I did accidentally put that in 3-volt. Okay, VIN for red is 3.3 volts. Ground for black, definitely on ground. Okay. So let's go back to guide page and see what's next. So we need the library. Let's get that open. Let me switch this over. This is other stuff. Should have had my should have got my PyCharm ready beforehand, but I didn't. There we go. And I'm just gonna start up serial. I'm gonna install the driver for the FRAM chip. Okay. And go back to here. Wrong thing. Let me actually do this as well. Okay. I have failed to disable the chat, unfortunately, on YouTube. So I will have to try to look into how to do that again. If anybody knows how to disable the chat on live streams that you are streaming on YouTube, please let me know. I would definitely appreciate that. Okay. Let's put the chat back here. And unfortunately, this, I don't know, this message looks a little bit spammy, but it's not as bad as some of the stuff we were seeing before, so I'll leave it for now. Let's grab the simple test, which is probably what's on this page. Probably should just close the camera controls because I'm going to click on that every time. So we're not using the write protection. So this is what we have. I'm going to scroll a little bit and just get the whole example code. That way we don't need to copy more stuff. What is this? This is Max 7219 stuff. I don't need this. This is a example from a different repo. Okay. D5 is our chip select, which is what we wired. Creating the SPI bus. Initialize the frame. Set a byte into the first index, and then read back from it. And read the first index specifically. This returns a byte array. Could write a sequential value, then read the values back. It allocates a buffer the size of length, which may cause problems on memory-constrained platforms. We're not doing anything else, and the RP2040 actually has a good chunk of RAM, so I think that will be an issue. In this case, it's listing 1 to 100 and storing that. So I guess in this case, it's starting at index 0, but because values is a list with 100 things in it, it's actually writing from index 0 to index 99 all the way. And then this would be reading it back. Interesting. So when you go to write to it, if you're writing multiple values at once, you still just write it as if you're writing to a single index, which is interesting. So let's see if this works. We can get the serial back. We can save this, and it will automatically reset. And we got a byte array, and we got 1 in it. And if we change this, it should change with us. So 7. We got 7 back out of it. So I think we got this working correctly. Let's go ahead and do the larger example as well. So we'll make values a list which contains range 0 to 99. And then we'll set it starting at index 0. And then we'll print all those bytes 0 to 99. It must be a single integer for a single address. So this does not actually work this way. But I suspect it would work this way. This is how NVM works. Yeah. Yeah. And I assume all this is right. I don't actually know off the top of my head, but of course we can tell the first bit of it here is right because it's counting sequentially. But of course the bytes are in hex, so some of them end up having, letters, and then eventually we run into bytes that represent ASCII characters, and so we start seeing those get printed as well once we're in the, the right range for that, essentially. So this seems okay to me. One thing we'll do is assume this came from the repo, and it seems like the example script needs updated since we got this error the first time. Yeah, I'm going to close this, otherwise I'm going to click on it every time. So let's go to the CircuitPython Fram library. Nope, not display frame. That is a different thing. This, and let's see if the same code is here. It is. So it's commented out, right? So when you run it the first time, it doesn't make any difference, but if somebody uncomments it, then it's broken. I'm gonna make an issue for this. If anybody is interested in making a PR, would welcome that and would happily review and get that merged. Example code. Too many entries or something? Data must be single integer. So example code single integer value error. In the simple test example, there is commented out code that writes multiple bytes to Fram device at once. This is Python code. And I edited it already, so let's get the actual code. Except this is Arduino code. Maybe we should just do this. Link to it instead of copy the code. Let's do that. Copy this. If you uncomment and attempt to run this code, raises this error. I think the line writing the data needs to include a slice of the proper length, like this, which is this. This is that locally. Seems to work, though I have very little experience with Frame. Okay, new issue. This way we can take care of this later, or somebody else could come along and take care of it as well. All right, what are these things? I don't think we need these open. Okay, so this is pretty easy. I've never used Fram before, but this is pretty straightforward. We initialize it, we write data to it. We can read data from it by just accessing the index we want to read from. You know, no problem there. I did some work on NVM recently, which is a similar type of concept, but it's built into the main chip, whereas this is obviously, you know, a separate thing that I have connected with wires. Most of these microcontrollers have a little bit of NVM storage, which works similarly to this. It's non-volatile. That's what NVM stands for, non-volatile memory. And you can save stuff in it, and it persists across power outages. So it stays there even when the thing is not powered up, which is the same thing that this does. So I did do a bit of work on that recently, and this is exactly how it works with that stuff. So I made a lucky guess that this is how it would be for this as well, since it's a similar concept, and it turned out that it seems to be right. How's it going, Keith? I'm doing pretty well for sure, and definitely hope the same for everyone. Okay. So, yeah, this is pretty straightforward. I think I got this down. This is exactly kind of what I was, expecting, hoping to find. The next thing I'm going to do is start looking into the EEPROM one. So that's this device, and it is going to connect over I2C instead of SPI. So that's one difference. It's luckily got stemma ports on it, so we don't really have to worry about all the individual wires. We're just going to plug in a little stemma cable. And I'm just going to double check. I don't think there is like a guide specifically for this yet, although if we make the library, then it stands to reason that a guide might follow. So I'm going to look into this, basically. We have these two files. And my C or C++ is not top-notch, necessarily. One of the things that draws me to CircuitPython is the syntax is a lot easier to understand, and there's a lot more stuff that is done for you that you don't have to worry about like you do if you're writing C++ code. So I can follow this to an extent, but it's not as though I can like actually necessarily read it and know exactly what it's doing. So we have a write object, we have a read object, we have a begin. Well, and these are not objects though, these are probably functions. This is dealing with the address only, so there's not a lot in this file. This is our default address, which is also mentioned on this page, I think. Yeah. So that's the header file, and we have this CPP file. We have a begin function, which looks like just initializes the I2C communication and, accepts the address. We have a write function where we're putting bytes into it. And this is not the I2C address, but rather this is the address where we're writing the bytes, I think. Getting shifted a little bit. Basically making a 3-byte buffer. Keeping the address shifted. Keeping the address unshifted. And then the value. And we are writing the buffer. Guessing this is length maybe, but I'm not sure. So we write this, it looks like if this does not return true, then we are returning false, which I presume means that we failed to write. So we're going to write this stuff first. We're going to expect that to return true, and as long as it does return true, then we're going to move on. One moment, let's... Okay, yeah, this is a follow-up from something I was asking about the other day. Or this morning, maybe? I don't remember when it was, but... Okay, so we write this stuff first. If it is successful, I assume, then this is going to end up returning true. Now we wait for a little bit. We have a timeout, 100, I'm guessing milliseconds, but I'm not sure. We're counting down. If the thing is detected, then return true. If it's not detected, then wait for a little bit and try again. and if it timed out, then we just return false. We failed to write. "16-bit address to write in memory, an 8-bit value to write at that address." So this is only writing 1 byte at a time. And we will eventually want to be able to basically mimic this type of behavior where we can write multiple bytes at once, but we're going to start with 1 because that seems easier. Here's our read. We give it the address we want to read from. It returns the byte that's at that address. Here is our multiple byte writing function. It also takes an address, takes a buffer pointer that points to a buffer that has the bytes we want to write, takes a number of how many bytes we want to write, so a length, returns true if it succeeds, false if it fails. And so this is basically just going to call write over and over again. So once we get the single writing and reading working, then the multi-writing is just a matter of calling write as many times as we need. This one's reading multiple bytes, which we will also end up implementing. It does, well, this one does work differently, actually. It looks like, do we have a read single? Yeah, we have up here, which is reading single. So interestingly, the write multiple just calls the write single over and over again, but the read multiple is actually its own function. It does not just call the read single over and over again. That's kind of interesting. Okay. So pretty straightforward. Begin, read, write. We're going to work on single bytes first. Let's see what we can do. Another thing I'm going to look at is the CircuitPython FRAM I2C example. I know the one we just hooked up was SPI, but this EEPROM chip is I2C. And again, I suspect we want it to behave pretty similarly to the FRAM one. So we'll look at the FRAM I2C driver, which is here, but it does extend this class up here. So let's start by doing pretty much the same stuff that we have here. Wraparound. I don't know what wraparound. Sure what that does exactly. Write protection, we're not going to mess with to start. Length we'll want, I think. At least eventually get item. This is reading bytes. If it's a single address, and if it's actually within the range that our chip has, create a buffer that's only a single byte large. Read the address, read from the address into the buffer. If it's a slice, this is where we would handle reading multiples. Set item, this is our write function basically. Checking the write protection. Again, we have the same logic. If it's a single int, then we're just writing a single byte. Check the data, make sure it makes sense. Again, make sure the address is in the range. That makes sense. And then just write, including wraparound. And then this would be the multi-bytes if it's a slice. Read address gets implemented by the subclass, and write gets implemented by the subclass. So I think we'll probably just kind of take this very similar structure, essentially. So I'm actually going to grab this file and start from it, and then we'll cut out the stuff that's specific to Fram, and we'll try to put in the stuff that the EEPROM needs. So I think I want to just start on the device. I think I'm just going to start on the device. Doesn't really matter what we call this at this point. Eventually it will either, like, I don't know if we'll have a separate library, or like, because the Arduino one or C++ one, they're both in the same library, but they're just different files. So for the CircuitPython one, we would either need to make another library for the EEPROM stuff, or we could put it inside of the Fram library that already exists, but we would need to separate it into different files. So make it like a module or a package. I'm not sure which of those is correct, but need to make it a folder, basically. Okay. So we're going to reference this. Let's see, where do we have all of our important addresses? Because we have, like, at the top of this file, we have a bunch of addresses and things. Manufacturer ID, product ID. We're not doing spam. We're not doing spy. So I'm basically just going to take out anything that is spy for now. But we might want to reference it, so I'll comment it. Okay. So we probably have a different max size. The Fram is 2 megabits, which is 256 kilobytes. And the EEPROM is smaller. 32 kilobits, which is 4 kilobytes. However, I don't know the units of this exactly. I'm not sure what the actual max size that we would put here is. This will all change. This stuff will change. But it's not important for, like, making it work, so I'm going to leave it for now. We will call this EEPROM. EEPROM. Again, we'll fix all the docs and everything if we get it working. Max size. It's interesting. Well, so we didn't have to initialize max size. Maybe is that only a spy thing? Because this doesn't do anything with max size. Max size. 27 matches. Okay. So the base class does have a max size. I2C class extends the base class. This one takes the bus, the address, the write protect pin. Doesn't take anything about max size. Super. Okay, it's just passing the hard-coded one. Okay. So we probably will need that, but I don't know the right value. I'll leave that. I'm going to leave the write protect stuff in. Am I going to do that? Does this actually, let's check. Does this one actually have write protection? Yeah, it does. has WP pen. We're not going to access it because we're just going to use the stemma port. So we won't be using it, but it does have one. And you could hook it up if you wanted to. So we'll figure out what to do with max size eventually. Write, protect, wraparound, I guess we probably need also. We'll be giving none here. So I think we can leave all of this code and it shouldn't do anything. Don't know for sure if we need this or this. Write protected, again, I'm gonna leave because it does have the write protected pin, but we're not gonna use it to start with. Length. This is one more than the highest address location that can be read or written to. It's the size returned by length. And so these were just hard-coded. The I2C one was 8,000 and the SPY one was 2,000. And 2 megabits here was 2,000. And this is 32 kilobits. So it's going to be less than 2,000. But how many bits are in a megabit and how many bits are in a kilobit? I don't actually know. 1 megabit in kilobits? 1 megabit is equal to 1,000 kilobits. So we had, okay, so we had 2 megabits, which is 2,000 kilobits, and we had 2,000 here. So this is in kilobits, should be. And on the EEPROM, we have 32 kilobits. So this would be 32 kilobits. I don't know what these are. We'll have to figure those out. This is going to return our max size, which comes from that constant. Oh. Well, it gets passed into the base class, but from the subclass, it gets hard-coded from the constant. Manufacturer ID, product ID. Do you know how we can read it, Dexter? Or I guess we could look on the, we could find a data sheet maybe? Are they used? It is used. Oh, okay, it's used to tell if we've found the device or not. So they get read from this. They get read from this. Okay. And again, folks, you will have to bear with me a bit because this is Again, the very first time I've ever kind of gone this low in the I2C stack to actually figure this stuff out. So we may not get there tonight. It may be slow going, but this is what we're working on. So I think the next thing I'm going to do is just comment out all of the SPY one, because I'm not doing anything with it and it's got a lot of red stuff. We can get rid of that. These things we can fix, EEPROM. This we can fix in here. Okay, so we have no more red. That's a good sign. Made one of these accidentally. So we will probably need to figure out the manufacturer ID and the product ID. Let's see if we have, let's see if those are in the Arduino code actually. ID, void, manufacturer. No, I think we're looping. Maybe this would be header though. Have the default address. Maybe inside a begin. No. So it looks like this one does not check if it's the right chip or not. So we have the address, but we don't have product, like manufacturer ID or product ID. We can find maybe this. Okay, that's promising. Yeah, that sounds like the same. Okay, we got different packages. We don't really care about those. So, again, I haven't done much like this before. I don't dive into datasheets too often, but we'll see what we can figure out. Init reads the values from the chip. You could just print what it reads. Yeah, let's do that. Let's do that. I like that idea. So we'll leave these for now. We'll find init, which is in the base, the subclass. One thing is, I don't know if it will be in the same spot as this, but let's find out. Okay. Whoop, don't want that. Whoop, product. So I suspect we'll hit this, but we should get our prints first. So let's start some testing code. I'm going to save this one separately. We want to refer back to it later. Like new CodePy. Then we'll basically just put the very beginning of this. I don't know if we'll need digital IO or not. This is the name we chose. So we're not doing SPY. We're doing I2C. This should be our I2C bus. Yeah. One thing I'll look at also is the SPY FRAM simple test. So we looked at, oh no, we looked at SPY. I'm gonna look at I2C though. We're just gonna use the default in this. This is all we need, I think. From I2C. Oop. I don't know if we need that, but let's do it. No pull. Okay, so I did not actually connect it, which of course we definitely need to do. So let's go here. I haven't even opened it yet, actually. I'm going to grab some scissors to cut it open real quick. I'll be right back. Okay. We are opening this. I don't need the pins. There's our little I2C EEPROM. I'm gonna unhook the RAM. And I'm actually just gonna take all these wires out as well for now. We'll leave that, no, I guess we won't leave that because it's kind of in the way of the stemma. Oh, that WoW key thing? WoW key thing is pretty cool. Oddbot. It does work with CircuitPython. Nice. Yeah, I was hoping they would add CircuitPython to that. I heard a little bit about it a little while ago. If folks are interested, the person whose name I don't know, unfortunately, but the person who I think is like the main person behind this project, this Wakwi, they did a really cool talk at Hackaday Remoticon. They talked about the internals of the ESP Wi-Fi. Basically, they were reverse engineering how the closed source Wi-Fi blob inside ESPs works. It was a really fascinating look at how reverse engineering things goes. Okay. What's this? I have high hopes for that project as well. Wakwi. I think we could ultimately I think we could be using that for automated testing. Okay. It's plugged in. There it is. Another thing I'm going to do actually is do a quick I2C scan to make sure we see address 50. I don't know the code for off the top of my head. I know where to find. I'll actually, for now, switch this. Okay, we did find 50. That's good. So we don't really need this stuff anymore. And this is all part of it. Actually, we don't need any of this. We're gonna go back to here. So we think this is gonna raise the error. And it did, but it's a different error. Bus device. One thing I'll do is update this. I don't know if I have the most up to date. Let's just update everything. I'm also on a weird build. Maybe I'll go to beta 1x. Guessing there'll be a bunch of these, and I think somebody showed me the flag for doing all these at once. Maybe it's just all or A or something. Fortunately, I failed to remember and I didn't put it in. So we're gonna do these one at a time. Hey Anthony, how's it going there on the YouTube chat? I'll let you know if you're still watching. The Discord or the Twitch is the best place if you do want to chat or ask questions or anything. I'm trying to kind of watch the YouTube one every few minutes, but the Twitch chat and the Discord chat I have pulled up on my screen, so that's the best place to go if you want to get questions asked or comments or anything like that. I'm gonna turn this back on. Okay, we still have a few more of these. Oh, major version. Yeah, that's fine. Chat's back here. There we go. Okay. All right, we got them all now. Okay, so we're up to date. I am gonna get the actual beta. We have this open already, actually. 710 beta 3. And I think I have UF2. Yeah. So we'll copy this. We will drop it on our board. This will put us on 710 beta 3. And that seems like a good place to start from. And while that's going, I go back to here. So what we found is this tried to connect at 7C for some reason instead of 50. Instead of 50, I guess. So let's see why that is. Knit 213. Yeah, so this is where it looked for some reason. And the specific line is actually on here, which is where it's trying to open. I don't know, where does this come from? I2C device, which is inside bus device. So why is this not using address? And does the I2C frame have the default address of 7.8? But I mean, we copied I2C frame and it defaults to 50 here. Well, and this is spy, of course. Not sure that it has a manufacturer a readable manufacturer ID. There is this, which is I2C. This is also the same size? No, different size. Versus. So this one says it defaults to 50 also. And I assume this works with the driver that we copied. But I am confused about where this came from. So what is write then read to expecting? Write then read into out buffer, in buffer, star. Out start, out end, in start, in end. We gave it only 2 arguments, and it looks like those are going to be out buffer, in buffer. So is this just the location? This is the address where the manufacturer ID and the product ID are stored on that I2C frame device? This one? What is the actual chip on this one? Can we find a data sheet for it? It's 65 matches. Device ID. Yeah. Check page 10, about halfway down. Is that where we're at here? Yep. Nice, thank you. Okay. So F8, this is where F8 came from. So we need to see on our EEPROM chip, do we have a similar ID, similar concept, I should say. We don't find device ID at all. What about ID space? Valid. Valid. Only valid. No other matches. So we might not have a place where we can just read the ID the same way. Looks like this data sheet is not super huge. Let's take a quick scroll through it. A lot of this stuff is going to be over my head, but let's see. My master can assign roles. So these are our pins which allow us to change addresses, which we do have, A1, A0, A2. Write data. Start condition on the bus and then broadcasts slave address with the RW bit set to 0. Master sends 2 address bytes and a data byte. Concludes by creating the stop condition. Slave sends acknowledge after every byte sent by the master. Stop starts the internal write cycle. While it's in progress, SDA output is tri-stated. And acknowledge. Interesting. Read operations. We have immediate read, we have selective read, we have sequential read. Ordering information, mentions, solder footprint, mechanical case, or dimensions. That's all. Okay. I think let's keep looking in the Arduino driver, which we assume is supposed to work. So do we have any magic addresses here? We have I2C main address. Hey, how's it going, Johnny? Thanks for tuning in. I hope you're having a good day. Figured out YouTube. So, you know, the funny thing is I thought that I had figured out how to disable the comments on YouTube. I found a thing that seemed like it was for disabling the comments, and I did that this week. But I do still have comments there. So I didn't do it right, or it doesn't actually do what I thought it did, or maybe I have to do it per stream or something. So I'm still not quite sure, but I did find something and I gave it a try. So we're hopefully one step closer. The object from memory. So we don't have any like inside of begin, which I assume is similar to init. We don't have any checking going on here it's actually like checking for a product ID or a manufacturer ID or anything like that. So my guess is this one just doesn't have it, probably. Just soldered up a PCB Christmas tree. Now I need to upload the firmware. Oh, that's pretty cool. Yeah, I saw a couple folks showed some Christmas trees like that on Show and Tell the other night. Those things look pretty cool. If you get it loaded up and get the LEDs turned on and stuff, it'd be cool if you want to share a photo. Be a cool thing to see. Or even if you don't, really, if you want to snap a photo of it before you got firmware, that's fine too. So read, when it reads, it is making a buffer with the address bit shifted and then the address normal. And then it is just calling write then read the buffer we created, the length, I assume, which is 2, the buffer again, then 1, which is the length we are reading, maybe? LED Christmas tree is this one? Sweet, yeah, let me pull this up here. Ooh, nice. I like that like stacking 3D effect going on there. That's a cool one. I should get something like this. I'll try these on Tindy. Couple Christmas tree, $30, not bad at all. Yeah, that's really cool. It's like a sculpture too. I really like the way it's different parts like that. And it builds up. So it looks like this is ESP32 based. Or, well, it says 8266. Maybe that's not a 32. And then RGB LEDs. Nice. And so then this has Wi-Fi on it. So I assume like with the firmware, you can maybe control it over the network or something like that. If you wanted. Sure, you could control it other ways too. Cool. Thanks for sharing. This is neat. All right, let's close this. So I guess let's just try to read. Let's try to read. So in our init, we're gonna not do D1 is mini based, 8266, nice. So in our init, we're gonna not do this stuff, basically. We're not gonna check at all product ID, manufacturer ID. We're just gonna create a device with address, which is 50. And we'll call super. And then what we want to do is try to implement read, which is, so we have read address, read buffer. Gets implemented. Okay, so I think read address is what we want. And we're going to worry about the like get item and slicing and all of that stuff later. I'm going to try to just get read to read a byte by itself. Oh, you tweeted about it a little bit here. Let's pull that up. Used to be 3. No Wi-Fi on this one. It's AT Tiny. Ooh, that's a pretty one too, though. I like it as well. Nice. Yeah, this is more like the one that those folks on Show and Tell showed, was a flat one like this. These are cool too, but I do like the way that other one stacks up. That's really cool. Nice. You're getting the getting all the festivities set up over at the Johnny household. Swapped out the star for a pink LED. Nice. So when we go to read, we give it an address, we give it a buffer, We get a write buffer. We're going to create it. It's 2 bytes long. We put the address into it, and we also put the address into it with bitwise math. I'm not sure the difference. I don't know exactly what these two are doing, but. And then it's going to go write, then read into, and then it's going to return the read buffer. So we would need to give it the read buffer. So this gets called from here, I think. Yeah. Buffer. It just creates an empty buffer. So what does it do if we just try first line is low byte of the 16-bit address, second line is high byte of the 16-bit address. Okay. That makes sense. So we have 2 bytes for our address, and let's see, where was I at there? That was down here. This is basically shifting off 1/2 and then the other half with these operations. Okay, yeah, thank you for the heads up. I do appreciate it. So we'll try, what if we just try print EEPROM 0? What does that do for us? We've restarted a bunch of times. Let's scroll down. Let's save this. Okay. We didn't crash. That's a good sign. We read a 0. I assume probably everything is going to be a 0. No, this one was a 1. Interesting. Well, not a 1, but a 2 Fs, 256, I guess, right? So our first byte is a 0, and then I'm guessing probably all the rest of the bytes are FF. Do we have enough yet? What happens if we do this? Does this work yet or crash? This works. It doesn't crash, and does look like all the rest of our storage is probably Fs. So let's look at, I mean, we don't have a great way to tell if that's correct. We're certainly reading something. Or well, we're getting something in our buffer at least. I assume we're reading because we're calling this. Let's look in write and see. Let's read this part here. Decided against using the chip's page write, since that would require doubling the memory usage by creating a buffer that includes passed in data so that it can be sent all in one I2C write. Single write method is slower and forces us to handle wraparound, but I feel this is better trade-off for limiting the memory required for large writes. Okay. And I'm guessing that, you know, one thing we should check maybe is, well, this doesn't do, where does it check the length and stuff? Is that up here? It is. Max size, which gets set from here, which should be getting set to our value here. So let's print the length also and make sure that that looks like what we put in it. Length of EEPROM 50 Seems odd to me, but maybe that is hex versus decimal. Is 32 in hex 50 in decimal? 32 hex in decimal? No. 90. No. None of these are 32 in hex. I could be doing this with Python. I don't know how. Hex converter. Hex number 32 or 50. It is 50. Okay. That does maybe make sense. So if we ask for 51, does it raise an exception? Does. And it tells us the range. That seems good. Ordinarily, we would be using probably not decimal, right? So we would probably have, 0x32 if we wanted to read the last byte. Or 31, rather. Which works. Okay. So far, it seems like we're reading correctly. Again, I don't think we can verify until we actually get writing working. Then we could write a byte and then read it back and see if it matches. So let's try to make the write work. Let's look into here. Write. What are we doing when we write? So we're creating a buffer that's 3 bytes. We're just going to write a single byte to start with. So our data is going to be an int. So we're going to go into here. Data length is 1. Data is a list containing only data. Start address plus data length. So make sure it's going to fit. Okay, wraparound, I guess, is if you tell it you want to write, 8 bytes of things, but you tell it you want to do it starting at 5 bytes from the end. I guess wraparound would allow it to come back around to the beginning. So it would write, 5 bytes at the end and then the other 3 at the beginning. That's my guess is how that works. I don't know if we have similar functionality on this chip or not. Wraparound. We do. Possibly. Maybe it just does it by default. I'm not sure. I think we want probably byte write, though, instead of page write, because essentially this says they chose to go with not the page write. So I suspect we should probably do the same here. So we're going to make sure to not go past the end for right now. If I2C exists, no, open I2C, I guess. Loop over the length. Make sure it's in range. Set up this buffer. This is again grabbing the top half of the byte and the bottom half. Well, it's 2 bytes and it's grabbing the first one and the second one. Thank you to Toddbot for that tip. So is this wraparound behavior? What is this? If not, Yeah, if it's not greater than the max size, this is what we're doing. Else, if it is greater than the max size, this is subtracting us back down. So this does look like it's the wraparound behavior. But for now, I'm just going to make sure not to write past the end of it. And it puts buffer 2 as data I, which is just our counter. And then it writes it. So what are the chances that this is the same thing we need? EEPROM 0. Let's put a 2 in it. And then let's print 0. Save that. No, unsupported. Unsupported operation at. Is this after the write? No. Yes. Interesting. So didn't we do that before though? Does this only fail if we wrote before? Hey, look, there's our 2. So I think we wrote a 2 into the first byte. That's pretty cool. Why did we fail? Why did we fail right after we wrote though? So get item. This is calling read address. The read address at 230 says unsupported operation from I2C device, and it's write then read into. So is there any hint in bus device about what makes an operation unsupported? Write then read into. Write bytes from out buffer to the device, then immediately reads into in buffer from the device. The number of bytes read will be the length of in buffer. If out start or out end is provided, which we're not, then the output buffer will be sliced. This will not cause an allocation. It also saves memory, so we're not doing any of that yet. In start, in end, we're not providing these either. But it says if we do, then the input buffer will be sliced as if in buffer, in start, in end. This will not cause an allocation. Okay. And so we don't have any like raise here. So I guess that's coming from whatever this is. Is this in the core? What is self.I2C? We're an I2C device. I2C is the bus that we got passed when we got created, which would be this, which is a bus IO I2C device. So let's look also for circuit Python bus IO docs. Okay. We are using this, but I'm just looking for the docs. And we're calling which one again? We're calling Well, we were back here in bus device though, which I maybe just went away from, did I? Yeah, got too many tabs open now. I think I went away from it. We're okay to skip past this one now. Bus device. Let's go back to here. Write to, then read from. Then read from. This is roughly the same stuff, right? This all, because we're basically just passing this through to bus IO. Does not say anything about like why it could raise that exception though. That's what I was hoping to find, maybe, was like raises exception if such and such, but doesn't look like we have that. So we got unsupported operation. Was it just not done, maybe? Maybe we just did it too fast? Like, we wait a second in between? Will we get the same problem? I'm gonna write a 3 this time. That one worked. So my gut instinct is that we were not done writing yet. My instinct is that we tried to write this by, we went to read it and it wasn't like done yet, basically. So we like kind of trampled on our write. That's kind of my guess. Again, this is my first time messing with any of this stuff this low level, so I don't know if that actually makes sense or not. But that is kind of what it feels like is happening to me here. And it does work fine if we wait in between. I suspect we don't need to wait anywhere near this long. Yeah, even 1/10 of a second is fine. Honestly, I bet we could go even smaller than this. Yeah. Even 1/100th of a second seems to be fine. So probably what we would do is inside of here, inside of, I don't know if this would be the same for SPY. I don't even know if there is a SPY one of these, actually. Do we need to worry about SPY at all? And I have way too many tabs open. From RFID, DAC. This is for something else. Does not look like they're like related products. What is this? I2C isolator. Buffer. Whoa, what is this? Has an SD card? Oh, it is an SD card, but it's like soldered. Whoa. I didn't know this existed. This is really cool, actually. 512 megabytes. SD card library. Huh. Interesting. Okay, rabbit hole though. This is not what we're looking for. I don't see any EEPROM that is SPY. This is the only EEPROM thing that comes back, and it's I2C. It doesn't work over SPY. I don't see any other products that seem like they would be EEPROM SPY devices. I don't think we need to care about SPY at all. So I'm actually, I think, just going to go back and delete all of this. And if one exists, we can write that part later. So really what we should do is, where's the right spot for this? Is it in the base class on set item, or is it in the subclass on the code that set item calls. And there was no sleeping in this already. I don't know. I think we'll put it in here. So if we put this in here, then we can take it out of here. Perfect. Okay. And we're actually getting the bytes that we're writing back out of it, so that's really, really cool to me. Again, I know I've said it a few times, but I've never done anything like this, so the fact that we're able to like write a byte into this thing, get the same byte back out, as basic as that is, that's really, really cool to me. So let's try the slice. Do we need anything else? So we're set item. This is the part we did so far. This is our slice. You're correct. Time is max 5 milliseconds on a standard EEPROMs. Okay, nice. Nice, that's good to know that like my instinct is actually makes sense and turns out to be the case in this. Okay, so 5 milliseconds, we could 5 milliseconds is 5/1000ths of a second. So we could make this even smaller probably, because this is 1/100th. So this would be 1/1000th, which is 1 millisecond. This would be 5 milliseconds. And if the standard write time, oh, it says max. Time is max 5 milliseconds. Is this from the this data sheet? 5 ms. Do we see that anywhere? Plus timing. ms, write cycle time, 5. Okay, and max is 5. So theoretically, we'd be safe after this, or do we want to go one more and make it 6? Seemed like it worked, but it does also feel like it could be the kind of thing that's maybe slightly different from time to time. Seems like it's working though. See. Seems like it's working. Okay. Where are my gloves at? Oh well. So what do we need anything else for slice? I think needs to be a byte array or a list. Checking the address. Slice stepping. I don't know what slice stepping means. Okay, check to make sure it's in the range. So is this in a, it's not really in a loop though. So I guess maybe the default behavior is to, if value is more than 1 byte, this will start here and just keep writing all the bytes it finds. Because it's not like it's in a loop and calling right over and over again. Well, at the slice level, I guess, but what is it doing inside of here? So we have right here. So this is what we did so far. This would be our slice. We get the length of the data. Check to make sure it's in range. This time, okay, we do have a loop inside of here. Data length. This, I think we said earlier, this is the wraparound logic. And so we are essentially just calling right over and over again. Yeah. So maybe this just works. Although we would probably want to wait each time we write, I suspect. So we would want this inside the loop. I think that makes sense. So I'm just going to save it, and I didn't change my CodePy, so this should write and read back the same thing. It did. That's good. We didn't break anything. Can we now go like this? 0, 1, and then 9, 3, 2, or 3. And then, so 0 would be 9. I'm going to do it this way for now, but we'll read the slice back in a minute as well. Here, let's try this way first, though. Save that. It worked. That's our 9. It matches up with tab, I think, or whatever this is. Our 3 is there. Seems fine. Seems fine. Let's do this. Yeah. Looks good. And so we could do more too, right? We could say 0, 3, and we could write a couple more like this, and then we could read them all back. 9, 3, 8, 1. Looks pretty good to me. It looks pretty good to me. So also another thing I'm going to try is let's turn this off, comment this out. No more writing. I'm going to save this. It's going to print the same things. We could turn off this probably now too. I think we know the length. I'm going to save it one more time. So we're just reading, and we have T, which is 9, 3, 8, 1. I'm going to unplug and replug the feather to make sure that it's actually persisting, right? Because the whole point of this is the storage persists even without power. So we're going to unplug the feather. We have no more power. We disconnected from TO. We're definitely off. All the lights are off. There's no way it's powered unless there's some really crazy stuff going on. We're going to plug it back in. It's going to rerun the same CodePy, and hopefully we're going to get the same output. Although I might have to restart it once because I don't think TO connects fast enough to catch it the first time. So breakout to REPL, restart. Perfect. It's still there. 9381. So it seems like it works. I'm sure there are some cases probably where it might not work, but the most basic stuff sure seems to me like it's working. We could try writing the whole thing. I mean, we know internally writing more than one is just calling write over and over again, so we would kind of expect it to work, I think. Eventually we need to figure out the wraparound logic, I guess. And I guess we would want to still probably figure out the write protection pin, like the way that pin works. But as far as like the basics of reading and writing, it seems like we're there. And we didn't really have to do that much. We pretty much just stole the FRAM code, cut out the part that was verifying it was the right chip, and the rest of this stuff all just seems to work. This part we'll want to figure out. The rest of this stuff seems good to me. It'd be cool if we had a way to do this, but it doesn't seem like we do. I mean, we are talking to the I2C address though, right? Like address 50. I guess it could be another device with address 50, but yeah, thanks, Keith. Let's just scan through this one more time real quick and see if I see anything that's kind of ID-like, basically, that we could read to verify that it's the actual chip we're talking to. Doesn't seem like it. Have 1 million erase write cycles, and we've used like 8 of them. We better slow down. Not really though. Frequency, these are all mostly times, it looks like, and voltages. Test conditions. So one thing is there are different, oh. Huh. 1010. Why is it called EEPROM if it's not actually read-only? It's a good question. What does EEPROM stand for? I don't actually know what that acronym is. I guess, yeah, ROM is probably read-only memory, huh? Electrically erasable, programmable, read-only memory. That's a really good question. Oats and honey, I don't know. Maybe this? Like, you cannot write to individual addresses. You can rewrite the whole thing, which kind of means it's not read-only in my mind, at least, but maybe they're saying that because you can't just write, like... But I mean, we are kind of writing 1 byte at a time. I guess I don't really understand all the way what's going on under the hood. Sure feels like we're writing 1 byte at a time, though, which sure feels like it wouldn't be possible if it were read-only. So that is a very good question. I think I'm just going to delete this stuff for now. And let's work on some docstring stuff in this. We don't need this. We don't need these. We don't need these. We don't need this. What does this want? 2 lines, maybe? 2 lines? Yeah. EEPROM. Let's fix some of this stuff. This is probably less interesting to watch, but it's got to be done anyway if we're going to eventually publish this. Determines if sequential writes will wrap around. Yeah. I'm going to leave this alone for now. We will eventually need to find out if that's actually something this chip does. There's references to it in the datasheet. Crap. Don't see anything here. I'm wondering if we have the max length right. I'm thinking maybe we don't. (32-byte page write buffer, but we're not using the page write. And so this, I think, is referring to how many bytes you can write at once. But this says 4,096 words of 8 bits each, which would be 4,096 bytes, which is 4 kilobytes. Which would be much more than the 32 that we had put here. So what if we try 33 and then print EEPROM 32? Does this go crazy on us or not? No, seems fine. Yeah, and we were able to write to it also. So I'm almost positive we don't have the max size right. But I'm not 100% sure what it would be. So the way I arrived at that before was we compared it to what we found in the existing CircuitPython Fram library. Let's look at the Arduino library that works with this already. See if it has anything about max. Not in this file. Max, not in this file either. Are there examples? Ooh, there's a validate memory. Interesting. Try to determine the size by writing a value and see if it changes the first byte. Starting on MAC address 1, ending all the way on 4Fs, incrementing by 1 each time. I believe it's because it's a type of ROM read-only memory. It's programmable. The EE allows you to electronically erase the programmable memory if you need to. Basically, it lives in the family of ROM devices. It's a type of PROM and is specifically EEPROM. Is different to RAM and the family of memory types. EEPROMs also have a limited lifespan of writes, which we did see in the datasheet, million writes, where you can expect to see degradation. Yeah, I do think that part's true. I think it said 1,000,000 writes, and then I think it also said 100 years, which I assume is like idle time, right? If you don't reach 1,000,000 writes, but you do reach 100 years, then it's also probably going to go bad. I won't be around to care, so. So this is interesting. This is basically just... This is basically just writing more and more stuff, and then reading back the first byte to see if it wrapped around. But I guess the question is kind of manually doing the wrapping. And this is all just based on the max size that we gave it. So if our max size that we gave it is wrong, then we're not going to be able to do this idea of just writing more and more and more and waiting until it wraps around to the first byte. Because it will wrap around after the max size that we gave it, which we think is not high enough. This is basically just writing some values, reading them back, telling us it's valid. Interesting. Right, multi-byte, right, objects. So the next thing I want to do after we make this library, of course, that's really the first thing, is to publish this library. Once we have this library, I would like to hook this up with message pack, the same way that I recently made a helper for NVM, so that we can store Python objects instead of having to worry about converting to and from bytes. I think that would be really cool. This is doing the same thing here. It's got that loop. It's checking if it wrapped around. This is dump the memory, but this is, again, just based on max address, which I don't think we have right. So how would we find the actual maximum is? What did we found 15 meters, millimeters. Oh no, but that's not bytes. Ratings, maximum ratings. These are all voltages. Or amperages. Input current. Capacitance. Clock frequency. Start condition, hold time. Low period, high period. Start condition, setup time. Data hold time, data setup time. Rise time, fall time, stop condition, setup time, bus free, between. So these are all times. All of these are times. None of these are number of bytes. Interesting. So it looks like write protect pin protects the whole thing. And if it's high, then it won't allow you to write anything at all. So we'll eventually test that out. We are using byte write. This is our page write, which is our 32 distinct data bytes. Hmm. Yeah. Um, so one question is this referring to the page size and this is referring to the total size? $47.18 is what I had for Fram. This says 2 M bits, 256 bytes. This does not seem like it's talking about page size on this one. Unlike Flash or EEPROM, there's no pages to worry about. So Fram, it looks like we don't do the page stuff. So I almost feel like essentially this is our maximum. We have 4,096 words. Each words is 8 bits, which is 1 byte. We have 4,096 bytes. And hex converter, or let me see if I can do this right. Is it just hex? Hex? Yeah. 1,000. I feel like maybe that's the answer. I think maybe this is 1,000. Firmware not behaving, probably need to troubleshoot the soldering. Oh, it's nice and blinky though. Nice. It's cool nonetheless. That's the thing with light up projects, like if it's blinky, it's good. The old name, it got the name following the family of memory architectures it was most similar to. It's completely different than RAM. As more features got tacked on, ROM, PROM, EEPROM, double EEPROM, it's gotten more distant from the original namesake. But that's the kind of the path it took to get there, so it kept the name. Makes sense. Nice. Yeah, that sounds like a reasonable interpretation of it to me, Keith. I've never done any like real specific courses or anything on it, so what if we try this now? I don't know what happens if we go like actually too high. I mean, I see here this is representing the max size, which is what the driver is limiting it by, is ultimately just this constant. What I don't know is this actual main chip, you know, this chip, C whatever, CAT24, C32, what happens if you write more than, like, what if you tell it to write to an address that's bigger than what it has? I don't know what it will do. Hopefully it won't, like, brick itself or anything. I only have one of these, so that would be a bummer. Hopefully that's not what it does, right? That's the cool part of computer science EE. You don't need coursework to figure it. Yeah, that's definitely true. Coursework doesn't always help. So many paths to making things work, and they're all valid. Yeah, that's definitely a good point. I'm very much a mostly self-taught. I've taken some courses, but the vast majority of my knowledge is like self-taught. Android is kind of my main. Android, and at this point I would say Django as well, Django Python, which is a web framework. Those are my two kind of fortes at this point in time. And the only course I ever took in Android was well after I already knew a bunch of stuff about how to do Android. If you do blow it up and need EEPROMs quick, Amazon has them. That's one thing. It looks like maybe Adafruit's still got some too. 44 in stock, and they're only a couple of bucks. I guess worst case is I could grab some more. Wouldn't be that big of a deal. So let's push it, I guess. What if we try 100? 7? Does this still work? Let's turn the length back on also, because this should now print a bigger number. Yeah, it probably won't blow up. Hopefully it won't blow up. This. Yeah, seems like we wrote a 7 to it just fine. Now our max is 496, which does make sense based on this. And it's definitely bigger than the 32 we started with, right? Otherwise we wouldn't be able to write this address and read it back correctly. So this should raise the exception because it's equal to the max. Oh, can't save from down there. Might have hard crashed. Maybe we did blow it up. This still thinks we have CircuitPy, but it's not actually responding. I think we hard crashed. I probably shouldn't have saved this into CodePy, huh? Because it's going to do the same thing when it comes back up. So we need to get to safe mode. Well, let's just try resetting. We have red. Yeah, well, it's not all the way hard crashed because this is blinking. It's not like dead. We did lose serial though. I can't break out to REPL. And I suspect this is never going to load the files anymore. So what if we just reset? Do we ever see disconnect, reconnect? Got CircuitPy back. Didn't see anything here. What? Oh. We're on ACM1 now. What is this? Control T, Q? I always forget this. Control to QT? Oh, that did it. Disconnected. 1. Oh, we are actually alive. So, whatever went wrong caused us to hang initially, but I pressed the reset, so it would have run again. And the second time it ran, it didn't cause the same issue. But we did end up reconnecting as a different serial device, so that's odd. What if we try... Well, this would be... this? What is 1 less than this? How do you convert back to decimal? Does this exist? No. Int? Is it just int? Yeah. Int. This is 496. $95. 3 Fs. No leading 0. Let's write a 4 to it. I saved it, but I'm still in REPL here. Ooh. No, we're stuck again. But that's odd, because it shouldn't have ran, because we're in the REPL. So we found maybe a different issue that made it hang? I feel like we found a different issue that would have made it hang, because while I did save this, it shouldn't have executed since we're in the REPL. Still supposedly connected as 1. We're not actually connected because I can't write anything anymore. Control Q? I guess it's just Control Q to break. Whoa. The TO is getting hung, not the board. Interesting. That's weird. Okay. We wrote the 4. Oh. I don't know why that's happening. But this should raise the out of range. And it did. So I'm thinking maybe this is the right size. I guess we could always, if we were feeling adventurous, we could try raising this by 1 more, and we could try writing the address of 1000 hex or 4096 decimal. And if it works, then we know it's actually bigger than this. But I'm a little scared to try, truthfully. Sketch up a little bit. Figured it was a historical name. Yeah. EEPROM is a big step up from having to stick chips under the UV. Yeah. I've learned about that before. Like watched a YouTube video or something. Clear window chips. Yeah, those little the chips with the windows are cool. So yeah, I mean, I think the way that we wrote and read from this suggests that we are at least this big. This is the minimum of the possible size, because this is working. We wrote the 4 into it. We're reading the 4 back out of it. We could power off again. So no power. Put the power back. We're not writing anymore right now. I turned off the writing. We're just reading. This will reconnect, but it's probably going to reconnect on this. Back to this one, 0. And we still see the 4 there. So we definitely wrote the 4 into this address, and it's saved and it's there. So we must be at a minimum this size. Okay. All right, well, I think Scott usually goes 2 hours. We're at about 2.5 right now. I think I'm probably going to wrap it up here. Obviously, there's still work to do. We need to go through this and, like, you know, change references to FRAM to EEPROM. We need to figure out if the wraparound, like, if we need to handle it here, basically, or if the chip does it itself. I suspect it probably doesn't do it itself, so we probably need to handle it. So we'll need to figure that part out. The write protection would be pretty easy to test. We could just pull that write protection pin to high, and then we could try writing to it. And if it fails, then it's working. The rest of this stuff seems to work pretty much as is, though, so we could touch up the wording here and there. You know, change stuff like this. Could be EEPROM. It's the name of a variable, so it doesn't matter, but it could be EEPROM. Obviously, the messages here, these could be EEPROM. The rest of this seems pretty good. Beyond that, it's basically just cookie cutter a new library for it, dump this code in it, and make the repo. And then we'd have a basic driver. So I know I've mentioned it a couple of times in the Discord about just asking if there's a driver for this thing, and I know a couple other folks have expressed interest in it. So I think it'll be cool if we can get this driver published, because it sounds like there are folks that want to use it. Yeah, is this a window chip? Give me the window chip. Yeah, these are awesome. I like these. I wish we had chips like this still. Even if they didn't need that, if they just put a window in it for fun, that's what I would do if I made chips. That's probably why I'm not a chip manufacturer, I guess, though. I think this would be sweet, though. But, all right, I think I'll wrap it here. I'm pretty happy. Like, again, this was my very first time messing with this low-level I2C writing and reading and stuff, and I didn't really make most of this code right. We just took this from Frame, and it basically worked without having to tweak very much, so that seems like a good thing for my first try, at least get my toes wet a little bit. Seems like it's working, so I'm pretty happy with it. Yeah, so my normal time streaming for folks that might be interested is Saturday morning. So tomorrow morning, 10 a.m. Central Time is what it is, which is what 12 hours plus 3.5 hours. So 15.5 hours from right now, whatever time zone you're in, 15.5 hours from now, that's, if I did my math right, which is not guaranteed, but probably pretty close. That's when I normally stream, Saturday mornings, and I will be streaming tomorrow morning, so that's the next time you can catch me. And Scott's out the next couple of weeks, but I don't know for sure if I have stuff going on Fridays or not, but if not, then I will probably stream in this slot again for the next few weeks while Scott is gone. So again, not 100% sure, but possibly the next few Fridays as well, but always every Saturday pretty much. And so thank you to everyone that watched. Anecdata, Toddbot, thank you especially for the help. Keith the EE, thank you for all the folks that shared the information from the datasheet. Johnny, I hope your firmware gets worked out, even though it is pretty cool now with the blinkies. Oats and Honey, thank you for all of the questions and stuff. Let me check on YouTube real quick. Nobody there, but thank you to Anthony and Emily who tuned in on YouTube. And yeah, I will catch you folks next time again tomorrow morning, 10 a.m. Central. That's the next time we'll be streaming if anyone wants to watch along. So thanks, and I will see you next time.